Okay, in the last video we left off with this slide about calculating a confidence interval. And essentially, you get a result from your sample, a mean or a percentage, let's say. You figure out the standard error for that statistic, which is a formula that I'm not going to go into here. Covered in the book, but it relates to the sample size and the amount of precision that you have given a sample size. And the larger sample size tends to produce more precision, and we'll talk about that shortly. So you calculate the standard error, and then you add and subtract two standard errors to the result of your sample, and that puts a boundary around your sample mean or a boundary around your sample percentage that represents, with a given level of confidence, typically 95%, your guess as to where the population parameter or the truth about the population is. So if you're estimating unemployment, the boundary represents your guess as to, with 95% confidence, your guess as to where the true unemployment rate is. Or if you're talking about an opinion poll, let's say something about, approval of the president, the presidential approval rating, there would be a percentage with the margin of error around it, which is this plus or minus 2%, plus or minus two standard errors, and that would tell you how, with 95% confidence, where you think the true percentage of presidential approval is in the population, if you could, survey everybody. Yeah. Quickly practice the interpretation of a confidence interval. We can take a look at this example in the book, which shows results from a actual NBC poll that was done of parental attitudes towards birth control in public schools, which is an important but controversial issue. So let's just go to this bottom part here. Do you think making birth control available for teenagers would not encourage them to have sexual intercourse earlier, or would it encourage them to have sexual intercourse earlier? So here's the split. 49% think it would not, and 46% think it would. Now, the missing percentage is the don't know, not sure, which are omitted from the chart. But now, if we look down here, we can see it's a survey of 1,000 adults taken in October 2007. This is an older survey. But here's the key part. The margin of error is 3.1%. So that tells us that we would now, I should point out the margin of error is not the same thing as the standard error. The margin of error is two standard errors. So if this is roughly 3%, the standard error would be 1.5%. Two standard errors equal the margin of error, at least at the 95% confidence interval. So that's how we get to the 3%, roughly 3.1% exactly, but we would add and subtract that to these figures. So let's look at the parents that think that, the percent of parents that think that this policy would not encourage earlier sexual intercourse. It's 49% plus or minus 3%, which means that the real percentage, had we somehow been able to survey all adult parents in the United States, the real percentage with 95% confidence would be somewhere between 46%, which is 3 below 49, and 52%, which is 3 above 49. So between 46 and 52% of all adults, that's our margin of error, our boundary, our guess as to the range in which the true percentage of adults at this point in time would or believe that the policy would not encourage early sexual intercourse. Okay, so that's a quick look at how to interpret a confidence interval. So typically when you see results like this, you see the results of the sample here. These percentages come from the sample. The notes or other documentation present the margin of error, and then, but to be a sort of a savvy interpreter of this kind of data, you would know to apply that margin of error to any of these percentages. Okay, so now a bit about what influences sample confidence intervals. Sample size is a big factor. The bigger the sample, basically, the more precision, and so the smaller that margin of error. So sample size and sampling precision are directly related. Confidence intervals and margins of error express sampling precision. And then the general rule is the larger the sample, the more precise the estimate. So in other words, the smaller the margin of error. So this was a sample of 1,000 that had plus or minus 3%. If we had a sample much larger, like 10,000, we might have a margin of error that's only about 1% or so. So it would go down. The bigger the sample, the more precise the confidence interval or the margin of error. And variability also matters too. So statistics that are more variable, like a 50-50 split, which is kind of like the example we looked at, has more variability, let's say, than a 90-10% split of the data. And so if the 90-10% split of the data turns out to have a smaller confidence interval than the 50-50. But one thing to know is that usually in reports like that, the worst case scenario is assumed, or as a 50-50 split is assumed. So the 3% margin of error is usually a conservative estimate, when applied to percentages that are closer to the extremes, like 10% on the low side or 90% on the high side. Okay, the margin of error or the confidence interval, but the term margin of error in particular, can lead to confusion because it seems to capture all kinds of error that might come up in a study, but it's not really that. The margin of error only expresses sampling error. So the margin of error does not include errors due to coverage problems like we talked about in a previous video, or non-response, or data entry mistakes, or misinterpretation of questions, or misleading questions, and so on. There's a lot of errors that creep into research. The margin of error is only really a formal expression of the sampling error, the error due purely to random variation in sampling. Okay, so one of the questions that comes up is how big a sample you need. You may be involved in doing your own studies or reports, or need to make decisions about sample sizes. Also, when you look at published studies, it's often of interest to judge the sample size. This is somewhat of a more technical topic at one level, but there's some basic ideas that are important to go over. And one is that the sample size depends a lot on how much you're going to cut into or break up the the data into subgroups. So subgroups, if you do a lot of breaking up of the data into subgroups, you need a bigger overall sample, because the precision of your statistics is driven really by the size of the subgroup, not by the initial total sample. So that has a big effect on the size, your need for a big sample size. So for example, if you want to look at men and women separately in a typical population survey, and you want a given level of precision, you may need twice the sample as you would if you're just going to look at the answers of men and women combined, because you would break the sample in half effectively. So if you start off with a sample of 1,000 and you break it in half, males and females, the separate answers or the separate statistics for each of those groups would only be have an effective sample size of 500, let's say. Now, another interesting thing is the size of the population does not affect the precision of the statistics or of the sample. So if a sample of 1,000 from the whole U.S. population, which is over 300 million, if that's at least, well, maybe 200 million adults, but if you 1,000 is a good enough sample for a population of 200 million, but if you live in a city or town that has only, let's say, 20,000 population, you would still need a sample of 1,000 to get, let's say, the plus or minus 3% that we saw in the previous slide. And that's kind of unfortunate if you're studying a small population, because it means you need just the same amount of resources and the same sample as you would for a big national study. It's good news, on the other hand, for national statistics, and it's one of the reasons that there are many more good statistics at the national level than there are at the local level, because it's simply more efficient to do a national study. 1,000 responses can represent the national population well. It's fairly expensive to do a sample of 1,000 if you're only looking at a small city or community. And When you calculate sample size, you have to take into account the response rate. And we mentioned a few videos ago that the response rates have been declining with most modes of survey data collection in the United States. They're often well below 50%, even below 20%. So you need to account for that. If you want to end up, let's say, with 1,000, you may need to attempt to reach or initially select even as many as 5,000, let's say. If you expect a response rate of 20%, you might need 5,000 households, let's say, to be randomly sampled in order to end up with 1,000 completed interviews. So those are all factors that go into figuring out the sample size. There's this formula here. It's not too bad. If you think of the margin of error as being like in our previous example, plus or minus 3%, you simply plug that into the right here. That's all that really needs to be plugged in. 1 is in the numerator. 0.03, let's say, is the margin of error we might want. We divide 1 by 0.03, then we square that. Here's the formula down here with actual numbers plugged in. 1 divided by 0.03 squared. It gives us a sample of about 1,000, which is sort of a little over 1,000. That's what we had. We were looking at in the previous example. Okay, so I won't say too much more about that, but you can look at the details in the book. But that's a quick, easy formula to do a rough calculation of